What's up everyone, Patrick here, welcome back, and in this next question we have to solve this system of equations over here. And the way that I'm going to go about doing this is with substitution, and notice that we have this y here by itself. There's no z value in this equation, and so if we isolate for this y, bring it over, bring the negative 3 over, we would end up with y equals 4x plus 3. And then this is a nice expression here with only two terms where we can take that and plug it in for this y and then have two equations and two unknowns. Now you don't necessarily have to isolate for this y. If you want to do substitution, you could isolate for this y, right? And then plug it in here, plug it in here. Different ways you can go about this. Just make sure that you're getting the same answer at the end. But this is the way that I'm going to do it. So I'm going to take this, and then I'm going to plug it in here and here. So starting with plugging it into equation 1, we'll have 5x plus 2 bracket 4x plus 3 plus 3z is equal to 4. So this would end up being 5x plus 8x plus 6 plus 3z is equal to 4. So this would end up being 13x plus 3z is equal to -2, like that. So that's one equation right there. And then I'm going to take it and plug it into the second equation, and we'd end up with 9x plus, the y is just by itself, so we would plug in 4x plus 3 there, plus 3z is equal to 1. And then from here, what would happen is we'd have 13x plus 3z, I'm going to bring the 3 over, and we'd end up getting -2. So this would be the second equation. But then notice that these two equations, what happens, they're the exact same thing, right? So if we were to find the x and z value here, or try to find it with substitution or elimination, what we would end up with is 0 is equal to 0. And whenever you end up having this in a question like this, it means that there's an infinite amount of solutions, right? So there's an infinite amount of points of intersections in this system of equations. Sometimes you'll see another term being used is that the system is dependent. And there's multiple ways to represent this. I'm going to show that in a sec, but just want to explain that whenever you get 0 is equal to 0, it means there's an infinite amount of solutions. The system is dependent. Because notice that, for example, if we did elimination, because everything is the same, this minus this minus that, this minus that, we'd end up with that 0 is equal to 0. Now, in this step, another thing I want to mention is that these equations, they're not always going to be exactly the same in an infinite solutions answer. So, for example, if we got like 13x plus 3z is equal to -2, for one of them, but let's say over here we ended up getting like 26x plus 6z is equal to -4. This and this, they're actually the same thing because it's basically taking this, multiplying it by 2, we'd end up with this over here. And so let's say that you got these two instead, and then you tried to find the solution between x and z with these two equations. Well, if you did elimination, let's say you multiplied this by 2, well, you'd end up with 26x plus 6z is equal to -4. And then when you subtract everything, you'd end up with that 0 is equal to 0 again. Right? So even though these two, they are the same, sometimes it's not going to be as obvious as this. Right? Maybe the coefficients are going to be different. They're going to be the same multiples, but the coefficients can be different then. Right? So sometimes there may be a little further algebra involved before you get to that 0 is equal to 0 point. But whenever you do get to 0 is equal to 0, it means there's an infinite amount of solutions. And then if you ever get to a point where, let's say, 0 is equal to a number, right? Or maybe like two numbers that are not equal to each other, some kind of inconsistency like that, well, then it means there's no solutions in the system. And another terminology for that is that the system is inconsistent, right? So you can have an independent solution, which is just a unique solution, just one point. You can have a dependent system where there's an infinite amount of solutions, where you would get 0 is equal to 0 at some point in solving. Or you can have an inconsistent system where there's no solutions, where it would be something like this. Usually like this. You'd get 0 is equal to some kind of number. And actually this, if we simplify, like bring the 2 over, we'd end up with 0 is equal to 5. So something like this always ends up being this kind of format, right? Whenever you get 0 is equal to a number, the system is inconsistent, and then there's no solution. Now, with a dependent system, there's actual ways to show these solutions. So we know that, I'm going to erase this over here. We know that when there's a unique solution or an independent solution, the system is independent, meaning that it intersects at one point. We actually have a point x, y, and z, right? Where these here are numbers. But with a dependent system, sometimes you'll see it in this format, but you'll see everything in terms of a variable. So let me show you. What we can do is we can pick a variable, one of these variables, x, y, or z, and then we can have the other variables in terms of that variable. Okay, so notice here how we have the y in terms of the x. So let's pick x first to make all of the variables in terms of x. So the way you could represent this is you can pick any x value, or sometimes you'll see this as x can be any real number. And then depending on what x you pick, then y has to be 4x plus 3. And then what if we were to make the z in terms of x? Well, a couple of ways we can do this. We could take this, because we have the y already in terms of x, and plug it into an equation. Another thing we can do is we could take one of these equations, they're the same thing, and notice that we just have z and x here. We can isolate for the z here. So if we do that, let me write this over here. We'll have 13x plus 3z is equal to negative 2. Well, to isolate for that z, bring the 13x over, so we'd have 3z is equal to negative 2 minus 13x, and then divide everything by 3. So we'd have negative 2 minus 13x over 3. And now z is in terms of x, so this would be negative 2 minus 13x all over 3, like that. But what if we did it the other way? So what if we plugged in this expression into one of these equations here for y, and then isolated for the z? Well, you'd get the same thing, because that's actually what we did before to get to this point. So if you did that, if you took this, plugged it into here or here, right, you'd end up getting to these points, and then when you isolate for the z, you'd end up getting that anyway. Right? So it could be shown, a dependent system can be shown like this. These won't be numbers, it'll be in terms of variables. So x can be any real number, the y would then have to be 4x plus 3, and then the z would have to be negative 2 minus 13x over 3. And that's why there's an infinite amount of solutions, because you could pick any real number for x. So for example, let's say we picked 1 for the x value. Then the corresponding y value would be 4 times 1 plus 3, which would be 7. Then the corresponding z value would be negative 2 minus 13 times 1, which would give us negative 15, divided by 3 would give us negative 5. So that would be a solution, one of these solutions for this system. And you could test this out. If you took this and plugged it in for each of these, you would notice that the left side would indeed equal the right side. That solution would pan out here. That's how you could check these solutions. Or let's say we picked another random x value. Let's say we picked 10 for x. Well, then the y value would be 4 times 10 plus 3, which would be 43. And then over here, we'd have negative 2 minus 13 times 10, so negative 130. So we'd have negative 132 over 3. And then negative 132 over 3, what does that simplify to? That simplifies to negative 44. Right? So that there would be another solution. You could test it out. If you took this point, plugged it in for the x, y, and z for all of these equations, you'd notice the left side would equal the right side. Now with these solutions here, you don't necessarily have to have this all in terms of x. You can have it in terms of y or z. And you got to be careful. You got to be able to get any of these, because you never know, maybe this will come up on a multiple choice test as the solution, as the dependent solution for this system. But maybe you'll get a solution on a multiple choice test where everything will be, for example, in terms of y. So then how would you know, right? If you got this, but then it's in terms of y, how would you know how to get that? Well, you just follow the exact same process. You use the equation. So if we wanted everything in terms of y, well, y can be any real number then. And then notice what we can do is we can isolate for the x here in this equation. So we'd have 4x minus y minus 3. So, equals minus 3. So we'd isolate for the x here, bring the y over. So we'd have y minus 3 is equal to 4x, then divide both sides by 4. So x would end up equaling y minus 3 over 4. So this would be y minus 3 over 4 like that. But then we need to get the z in terms of the y as well. And we can't use these equations here because this was in terms of x and z, right? So when we isolate for the z here, it was in terms of x, but notice there's no y here. So we can't use this equation, these equations here, to get the z in terms of the y. What we have to do is we need to take this, we already have the x in terms of the y, and plug it in to one of these two equations and then isolate for z, right? So there's going to be more algebra in this one. So if we did that, I'm going to erase this over here. If we did that, what would happen is, let's use the first one. So we'd have 5 bracket y minus 3 over 4 plus 2y plus 3z is equal to 4, like that. And now what we would do is we'd have to isolate for the z. So what can happen here, different ways you can do this. The way I suggest doing it is if you get a fraction like this within, I'd recommend multiplying everything by the lowest common denominator. So notice this is all over 1. We have a 4 here, so multiply this by 4, multiply this by 4, this by 4, this by 4 to get rid of this fraction. So the 4's would cancel out here. We'd have 5 bracket y minus 3 plus 8y plus 12z is equal to 16, like that. And now notice how we have an equation just in terms of y and z, and we could isolate for that z. So the way I would do that here, 5y minus 15, expand that bracket, plus 8y plus 12z is equal to 16. And then from here, bring the negative 15 over. So 16 plus 15 would give us 31. So we got rid of that. Then this would be 13y. Bring that over. So that would be minus 13y. and then we could divide everything. We'd have 12z over here left, and we could divide everything by 12. So z would end up being 31 minus 13y all over 12. Right, and you can't simplify that any further, so 31 minus 13y all over 12, like that. So that's another way to represent the solution for this dependent system. And in this case, you could pick any y value. So if we picked 1 for y, and then we plugged in 1 for y here, 1 for y here, we'd get a point that would again work as a solution to this system. And you could pick any y value. All right, so you got to be careful with these dependent systems, different ways to represent the solution, right? So we could represent it in terms of x, in terms of y. What if we wanted to represent it in terms of z? Well, then things are going to be a little bit more complex. The algebra is going to be a little bit more complex, because what was nice is in terms of the x and y, we had this equation, this easy equation to play with where there were less terms. But now if we're going to isolate for, or we're going to make everything in terms of z, we're going to have to be using these over here. So you could do this in steps. We know that we're going to have z by itself. What we can do in this case is we can actually use that equation that we got before, where we had, what did we have before? We had 13x plus 3z is equal to -2. Right? That's what we ended up having when we took this and plugged it into both y's. And so notice here how we can isolate for the x and have it in terms of the z. So in this case, bring the 3z over, so we'd have 13x equals -2 minus 3z. Divide both sides by 13, so we'd have x equals -2 minus 3z all over 13. So we have this portion now, -2 minus 3z all over 13. But now what's remaining is to get the y value in terms of the z. And the way we can do that is we can take this x value in terms of z and plug it into either equation, right? And then we'll have everything in terms of y and z. So I could take this, either plug it in for this x or this x. I'll plug it into this one. So we'd have 5 bracket -2 minus 3z over 13 plus 2y plus 3z is equal to 4, like that. And now notice we have everything in terms of z and y. And so when we isolate for that y, it's going to be in terms of z. All right, so again, there's multiple ways to go about this to get these solutions that I'm writing out. Just make sure that whichever way you do go about it, you're getting the same. The final result should always be the same, right? After you simplify, everything should be the same. The solutions should be in the same format. So over here, we'd have what? 5 minus 2 minus 3z. This is going to be all over 13. So I think we're going to follow what we did before, where we multiply everything by the lowest common denominator. The lowest common denominator in this case is the 13. 13, multiply this by 13. So these 13s go away, so we'd have 5 bracket -2 minus 3z plus 26y plus 39z is equal to what? 52? 13 times 4. And then we would, what are we doing? We're isolating for the y, right? To get it in terms of the z. So we'd have -10 minus 15z plus 26y plus 39z is equal to 52. And then from here, we just have to solve. So bring the negative 10 over. 52 plus 10 gives us 62. 39z minus 15z would give us 24 rather, sorry. Z plus 26y, like that. And actually, we can simplify this. We could divide everything by 2. And so we'd end up with, I'll continue this here, 12z plus 13y plus, or equals rather, 31. Right, like that. And we're isolating for the y, bring the 12z over, so we'd have 13y equals 31 minus 12z. Divide everything by 13, so we'd have y equals 31 minus 12z all over 13. And so now we have the y in terms of the z, and that would go over here. So that's another way to represent this if we made everything in terms of the z. So you can make everything in terms of the x, y, or z. You have to be able to do all three in case this is a multiple choice answer and they give you only one of those solutions. You got to be able to go. If you notice that the multiple choice, let's say it's all in terms of z, the solutions, you know that you have to go about it this way and see which one it's going to be. And then with these kinds of solutions, you could test them, right? Remember, you could always test them. In this case, if we picked, again, a simple one to pick is 1. You could pick any real number for z. If we plug in 1, negative 2 minus 3 times 1 would be negative 5 over 13. If we plugged in 1 over here, 31 minus 12 times 1 would give us, that would give us, what, 19? And so we'd end up with 19 over 13. So this here would be a point of intersection, and then you could test the point by taking this x, y, and z, plugging it in for all of these equations, making sure the left side is equal to the right side. Right, so lots in this video going on. First off, when you're solving, if you get 0 is equal to 0, the system is dependent, meaning there's an infinite amount of solutions. And then you got to be able to, if they ask for it, make a general formula for the points. And you got to be able to make it in terms of the x, y, or z.